If you suspect fraud is occurring in your business, you need to watch this video. I'm going to show you a simple way to detect fraud in your transaction data using nothing but a spreadsheet and an obscure law of mathematical probability called Benford's Law. Forensic accountants use this technique frequently, and so can you. This video was made using Microsoft Excel 2019. Benford's Law is also known as the Newcomb-Benford Law, the Law of Anomalous Numbers, or the First Digit Law. In 1881, a Canadian-American astronomer made a casual observation when he noticed that his books of logarithms tended to have pages more worn and coffee-stained at the beginning than at the end. And those beginning tables of logarithms contained logarithms that began with the digit 1. This casual observation led that astronomer, named Simon Newcomb, to the conclusion that when you have a set of truly random numbers, you tend to get more numbers beginning with the digit 1 than with the digit 2, and more numbers beginning with the digit 2 than 3, and so on down the line, with numbers beginning with the digit 9 being the least frequently observed of all. Later in 1938, physicist Frank Benford presented the law of anomalous numbers formally in a paper, and Benford was eventually given credit for this discovery. This is Benford's distribution presented graphically. You can see the first digits across the horizontal axis at the bottom. The digit 1 is expected to occur about 30.1% of the time, and the first digit of 2 about 17.6% of the time, decreasing all the way down to the first digit of 9, which is only expected about 4.6% of the time. It's important to understand that Benford's distribution does not apply to all data. For example, if you took a list of 10 or 7-digit phone numbers in the United States and tried to apply Benford's distribution, it wouldn't work. There are artificial constraints in play on the area codes and the prefixes of those phone numbers. Conversely, if you took the length of every river in the world measured in any unit of measure and applied Benford's distribution, it would work quite well. Those numbers are completely random. Benford's distribution is known to work well with sales transaction data as well as purchasing transaction data. And it works very well when you have combinations of numbers being multiplied or added together to form the final number. Benford's distribution tends to not work very well when numbers have a built-in minimum or maximum, they're rounded off, or they're subject to some sort of psychological threshold, like everything ends in 99 cents. So the first thing you need to do is to consider carefully whether any of those constraints are in place on your transaction data. Keep in mind, you may have a policy in place such as all transactions over $1,000 need manager approval, which will influence your employees, but that's not a constraint on the actual transaction amount if everybody's doing their job and being honest. I will say, however, that fraudsters are typically influenced by such rules, and transaction data entered by fraudsters doesn't conform to Benford's distribution normally unless it's a very clever fraudster. We're going to use a 4-step approach to attack this problem. First, we need transaction data, and we need that transaction data broken down by employee if we suspect that one of our employees is committing fraud. Next, we're going to chart Benford's distribution, and we'll be adding things to this chart in the next steps. In step 3, we'll determine our desired confidence interval and add that to the chart. Finally, we'll analyze our transaction data. First, we'll look at all employees grouped together, then we'll analyze individual employees. In this scenario, we run a department store. We have different shifts of employees working at the department store. And on one of the shifts, we've identified that we have some inventory shrinkage. We have some unusual inventory variances that we've isolated to this one shift. There are 4 cashiers who work on this shift. We'll just call those cashiers cashier A, B, C, and D. There are thousands of items sold in our department store, and any combination of them could show up at the cashier for checkout. We sell food, beverages, clothing, sporting goods, and so forth. The only constraint on our cashiers is that any transaction over $100 needs to be approved by a manager. With Benford's distribution, the more data you have, the better. So we've downloaded a report of sales transactions processed by these clerks that numbers about 6,000 transactions. So this is our data. This is a transaction by employee report. And these are the cashiers A through D and their transaction amounts. This particular report is sorted by amount, so it starts out with very low transactions, maybe somebody buying a candy bar, and they go down to transactions that are quite large, but they're all under $1,000. So that's our data. All we need to do now is isolate the first digit of each transaction. So we can do that with our left function. Go to 1 digit. And I'm going to autofill that down. That seems to be working just fine. So I'm going to go ahead and copy this column and paste as values to cement those in there. And I'm going to ignore the error. So we've isolated all the first digits. Now keep in mind, this is a very sanitized report. This report may have many other data fields on it. I cleaned it up. It would have had the time of day and the date and which cash register number and many other things on it potentially. All we really need is the cashier and the amount. Our next step was to chart Benford's distribution. So I put the digits into a table here. These are just numbers in a cell. And this is Benford's distribution for each number. So 1 should be 30.1% of the time. And I took these out to 5 decimal places. All of these distributions should add up to 1 or 100% if you want to think of it that way. And they do. So let's quickly throw a chart in here that will show our Benford curve, if you will. And that looks pretty good. This first one is going to be for all cashiers collectively. So I'm going to call that all cashiers. Now, without getting too deep into the statistics, this curve is not enough. We know that in our sample size of nearly 6,000 transactions, that's a pretty big sample, but we're probably going to have some deviation from these exact amounts. It's inevitable. So how much of a deviation are we willing to tolerate? That's where z-scores and confidence interval comes into play. So there's a formula to calculate the upper limit and the lower limit of our confidence interval. And I'm going to choose a confidence interval of 95%. Think of the 95% confidence this way. This list of transactions is a sample. It's not the entire population. So how much faith can we put in this sample data when we're trying to make a judgment about the whole population? So what we can say is that if we have a deviation from the upper and lower bounds we set on this Benford's distribution, we can be 95% certain that the entire population deviates as well. Conversely, if our sample data fits within our upper and lower bounds at every digit, we can say with 95% probability that the total population conforms to Benford's distribution. Before I put the formulas for the upper and lower bounds on here and plot those, we're going to need 3 items, and I've added those to the bottom of our gray area here. One is the expected frequency, or P sub E, of each digit. So that's right above in column F. I'll just call that Benford's distribution. Now the sample size in this sample over here is 5,946. So that'll be our sample size for this one, which is going to be all the cashiers. We're going to look at the cashiers individually later on, but for now, that's 5,946. And the Z value for a 95% confidence interval is 1.96. That's a statistical constant. If you want to change this to 90% or 99%, there's a different constant you can use, and I'll let you guys go look that up on the internet. So let's compute the upper limit or upper bound and lower limit. I'm going to move our chart slightly because I'm running out of room, and paste in right here the formulas. Don't be intimidated, these are not that hard. So the upper limit will be right here. Let's read across from here. Equals P sub E plus our constant of 1.96, and I'm going to fix that value, times, and I've got a square root item here, so I'm going to put that in parens. It's going to be P sub E times paren 1 minus P sub E again, divided by n, which I will fix, close paren, take the square root, you do that with a little caret, put 1/2 in parens after that, and then we've got to add back the 1 divided by 2n, and I'll fix that n. So we come up with an upper limit of 31277. That seems like a reasonable answer. So I'll show you a neat little trick here. Since these formulas are virtually identical, except for the 2 minus signs and 2 plus signs, I'm just going to paste this formula over here for the lower limit. And I need to change all these G2s to F2s because that's where my P sub E is. So I'm going to find the G2s and replace with F2s. Should get 3 replacements, which we do. So now I've got the same answer as here, and I need to just change these to minus signs. Saves us a little time. So that seems like a reasonable answer there. My lower limit is below my Benford's distribution number, and my upper limit's above it. So let's paste these down. And it looks like all of them turned out that way. So I'm going to assume we did that right. So let's pull down our chart and add those 2 series to our chart. In fact, let's get rid of this stuff since we don't need it anymore. And we want to select data. I'm going to first edit this series because I never gave it a name, and I'm going to call that Benford's distribution. And I'm going to add another series and call it upper limit. Those values are right here. And let's add one more, call it lower limit. So there you have it. We've got our upper and lower limits there. Now, I'm going to make this chart bigger so we can see, but basically the idea is we're going to plot our actual transaction data on here, and I'll probably use a different kind of chart for that, probably a bar chart. So we'll have a combination bar and line chart when we're done. So let's go ahead and see how it looks. So next we want to get the distribution among all cashiers of the different digits and plot those on this chart. So I'm going to create a couple more columns here in order to do that, and expand my gray area here with my data. I'm going to call this one the digit count, and I'm going to call this one the digit frequency. So what I want here is for the digit 1, I want to count all the ones in this column over here. So I'll use a COUNTIF function. And I want to count in the range of C2 to C5947. And my criteria is simply equal to 1, and you have to put that in quotes. Let's fix these references so I can paste down. We still have a little work to do on these, so let's change this one to 2, this one to 3, this one to 4, and so on. So now I need the frequency. Let's sum these. I'll put a line there. That's the number we would expect with that many rows. And the frequency distribution of this digit is going to equal this divided by this. And I'm going to fix that reference. Take it out to 5 decimal places. Looks like I've got 6 there. So there is my digit frequency distribution, and you can already see we've got a little variance from Benford's distribution here, but it looks reasonably close. Let's see what that looks like on the chart. We're going to add a series to our chart, so I'm going to select data, and let's add a series, and we'll call it all cashiers. My values will be right here. And let's throw that on there. So that's all lines. We want to change our chart type. So let's right mouse click in the chart area here, and you get this change chart type option. And if you go to all charts tab, there's a combo chart down here. Now, this is actually not what we have selected right now. For the Benford's distribution, I'd be okay with a smooth line, just a regular line. For the upper limit, I think I'm going to go with the line with markers, as well as the lower limit. And for the all cashiers, I want a bar chart. Let's see how that looks. Now, I'm not crazy about this color. I'm going to fill those in gray. I'm going to resize this chart and we'll take a close look at it. I went full screen mode for this part of the video. And what you want to do is go down through each digit. Here's the digit 1. And it looks like we're very close to the middle of our upper and lower range there. 2 looks good. 3, 4, 5 is close to the bottom, but not quite. 6 is a little better. 7's a little better. 8 is quite close to the upper limit, and 9 is the one digit that is actually over the upper limit. And you can just confirm this by looking at our data. This distribution for 9 on all cashiers exceeds the upper limit here, and this 8 is perilously close, but it's within bounds that we set. So what do we do in a case like this? We do have reason to believe that there could be fraud. And let me make it clear, this deviation from Benford's distribution is not proof of fraud. It is reason to suspect fraud, however. So let's proceed on. And the way we're going to proceed on is to look at each cashier individually and see if any of them break out as individuals. To analyze each cashier individually, I've added a set of 2 columns for each cashier to my table of data. So we need to count the 1 digits for cashier A only. And we're going to use the countifs function there, because we have 2 criteria. We need to see an A here and a 1 here. So my criteria range for my first criteria is going to be A3 to A5948 because I added a row. And the criteria I'm looking for is in quotes equals A. Now I have to enter my criteria for range 2, which will be column C over here. So that'll be C3 to C5948. And that criteria will be in quotes equals 1. I'm going to fix all of those references so I can paste this formula down. I get 469 for that one. And like before, I have to change these. And we'll get a sum here. And my frequency distribution is going to be this, well, equals this divided by my sum, which I will fix the reference for. So there's my frequency distribution for cashier A. I'm going to go ahead and repeat this exercise for the other 3 cashiers. So a really easy way to do this is to just simply copy cashier A's data and formulas over here. And then ask yourself, what's changing here? We still want to look for 1s in the same range. The only thing that's really changing is this equals A needs to be changed to equals B. So I'm going to use the find and replace feature. And you got to be careful here. We have an equals C right here. So when we get over to this column, that's going to be a problem. So I'm going to put equals A quote so I don't catch something unintended. And I'm going to replace that with equals B quote. Now I should get 9 replacements, 1 for each cell. So it looks like that worked okay. Now we've got a sum here. That's fine. I'm going to ignore this error. And we need to check this formula. Remember, we made this cell an absolute over here, and we don't want that. So we're going to have to change all these K12s to M12s. So once again, use your find and replace $K, $12 to $M, $12. Should get 9 replacements. As kind of a final check, these columns of frequency should always add to 1. So you want to make sure those are adding up to 1. I'm going to go ahead and repeat this exercise for columns C and D for those cashiers and then check back. So I've set up my counts and frequencies for all 4 cashiers. But there's one little fly in the ointment that has cropped up. Remember these upper and lower limits and the formulas? And I'm going to paste these formulas back in here to take another look at them. One of the inputs for these formulas was N, the sample size, and we used 5,946 because collectively the 4 cashiers had that many transactions. Because each cashier basically split those 5,946 transactions roughly evenly, we need to reestablish N. Now, technically, I should recompute an upper and lower bound for each one of these cashiers, but they're all pretty close to 1,500. I'm going to take the average, which is 1487, and I'm going to use that as my N and recompute some new upper and lower bounds for each cashier. So I think the easiest way to do this and remain organized is going to be to insert a couple columns here, and I'll bring these over and paste them in here. And instead of all cashiers, we'll call this individual for the individual bounds that we're going to use. Keep this relatively organized. So for my upper limit, what's changing now? Really, I'm just replacing these N's in the formula, which is this $H, $14, with a number which we said was going to be 1487, the average. So let's go ahead and do that in both sides here simultaneously using find and replace. $H, $14, and we'll replace that with just a simple number. Should get 36 replacements because I had that number appears 2 times in each formula, and there's 18 formulas. The other thing we need to change in these new upper and lower bounds is the reference to P sub E. Remember, that was a relative reference in our formulas over here. It references F3, the Benford's distribution column. So we need to change all of these J's to F's. Let's see how that works out. We should get 3 times 18 or 54 replacements. 54 replacements, good. And now we have established new individual upper and lower limits, and you can kind of tell by looking at these, they're a little wider because of the smaller sample size. This goes from 0.277 to 0.324, whereas with the larger sample size, it's a narrower range of values. So my next order of business is to create a chart for each cashier and evaluate them as individuals. I think the easiest way to do this, since I already created an all cashiers chart, is to simply copy that one, and I'll go down here a little further and paste it. And we'll rename that as cashier A. And we'll just go in here with a right mouse click and change the data. So the Benford's distribution line will remain the same, but the upper limit is going to change to this individual upper limit. So let's go into that one and edit it. The name is good, but the data needs to be right here. Then we need to edit the lower limit. The name is okay again, but the data will be right here. And I need to edit this one a little further. Instead of all cashiers, we're going to call this A, because that's what will appear on any legend that I decide to do for this chart. And the values are going to be right here. So let's take a look at that chart. And I've got an undesirable color there. I'm going to change that to a nice muted gray. So cashier A, how does this cashier stack up? For the digit 1, it looks like the cashier is in limits. 2, 3. It looks like this cashier is well within limits. So I'm going to go ahead and repeat this exercise for cashier B, C, and D, and then we'll take a look at all of them. So I've completed my charts and I kind of standardized them a little bit. I made the upper and lower bounds the same color. And we already looked at cashier A. Cashier A looked like that person was in limits. Let's look at cashier B. I see some minor deviations from Benford's distribution, but again, given the sample size and the tolerance that we've chosen, it looks like this cashier is in limits. How about cashier C? As you go down through the digits, there's some deviation again, but looks good. Cashier D. This cashier has an unusual and unnatural disproportionate percentage of transactions that begin with 8 or 9. This is a little suspicious. This is not proof of fraud, but it is definitely something to look at with cashier D, especially in light of the fact that we have a $100 manager's approval threshold. I wonder if this cashier has an accomplice who's coming through the line at her cashier every day and she or he is not ringing up all of the items and keeping it under $100. So that is definitely something to look at. That's how to apply Benford's distribution to some sales transaction data. If you've enjoyed the content of this video and you'd like to see more like it, please hit my subscribe button. I will be releasing one new video a week minimum for the foreseeable future, and you can learn about Excel and expand your Excel skills. Thanks for visiting Spreadsheet Geek.